Hello everyone and welcome to a new discussion of this groundwater engineering course, and today we are going to discuss permeability. If you recall, in previous discussion when we were discussing about porosity, little bit we touched also about the permeability, because both parameters are very well connected. So, that is why the continuity is very much required. So, as you know that the porosity is the description of how much space there could be to hold water, and this we are talking about in the underground conditions, and whereas you know the permeability describes how those pores are shaped and interconnected. So, let me give you a sort of analogy, though it is not very befitting, but just to understand that if there are lot of poles are there and if they are not connected, then the communication cannot be done. So, similarly here the pores are our poles here, and this if interconnections are there, interstices are there, then the permeability will be there. So, interconnections is very much required among the pores, gaps, voids or fractures or cracks, whatever in the rocks, then only permeability will be there. So, it permeability specifies that how is it to water to flow from one end to another or one pore to the next, and we know that it is a quite slow movement depending on the rock conditions, that we will see also, and some other parameters which we will also discussing in later in this one. So, as we have also discussed while discussing the porosity, that when we are having larger pores space, and that means there will be less friction, and of course other like viscosity of water will not also play major role, and between the flowing water and the sides of the pores. So, a large pore space always will promote the high permeability, whereas you know contrary to this the smaller pores means more friction along the pore walls, but not also more twists and turns for the water to have to flow through. So, large pore spaces, especially in large grains, that is the high possibility we can expect better permeability. So, like a permeable material, that can be a natural rock or soil or loose sediments or alluvial deposits like that. So, permeable material has a great number of large well connected pore spaces, whereas in impermeable material like hard rocks, where there are might be few smaller pores and that are poorly connected. So, which drastically affect the flow of water and poor permeability. Permeability, as we have been discussing, that is the ability of a rock or a soil or whatever to allow the passage of fluids, and fluid here of course we are talking about water, into and through it without weakening its structure. So, it does not harm unless the water is polluted or some other chemical impurities are there. Otherwise, the water when it flows through these pore spaces, then there is no harm to the structure. Permeability is also most important variable in groundwater, because as when we were discussing the porosity, there a rock might be highly porous, and like I gave the example of clay or which is sediments, but like shales. So, they may have porosity, but they do not have the permeability, and therefore, this parameter, this variable in case of groundwater studies, that is the permeability, is the most important one. Permeability also describes that how easily water can flow through the rock or unconsolidated sediment. So, when I have been giving several times examples of Indo-Gangetic alluvial plain, which is a huge land part of the country, and also there are some other parts in which we are having alluvial fills or valley fills, there the permeability is going to be very high, and how easy it will be to extract the water. If permeability is good, then there are chances that we can extract water, exploit, or we can develop a well which will give us a good yield if permeability is good. So, in depending on the type of material, so permeability of a particular material is defined by its coefficient of permeability. or we also call as hydraulic conductivity. So, the conductivity here means because it has to water has to flow from one pore to another or from one place to another, one end to another. So, it is the flow in the cubic meter per second through a unit cross sectional area of a material. Why cubic meter per second is because it is a 3D body. So, therefore, all three dimensions have to be taken in this account, and therefore, you can have per minute, per hour depending on the permeability, but if we keep permeability per second in case of highly porous material, these are just changes in the unit, nothing that much important. Now, this characteristics of permeability of a geological material, which is can be quantified by engineers or geoscientists using a number of different units, but the most common one is the hydraulic conductivity, and the symbol which is used in the literature generally for hydraulic conductivity is K. Now, this hydraulic conductivity can also be expressed in range of different units, but we shall be using a meter per second in our in this course or in all discussions. So, let us see the another related parameter, which is the transmissivity. So, transmissivity, as you can see that the say schematic is there. So, water is flowing from this 3D body. So, this part is of course the water saturated, the top part is impervious, as you can see. So, this is the thickness of the layer, which is in terms of meters. So, m, and below this is also impervious. So, this scenario is about confined aquifer conditions, and then width is also given here. So, transmissivity we can define here is the rate at which water passes through a unit width of the aquifer under a unit hydraulic gradient. Now, gradient if it is flat, of course, the transmissivity is going to be less. If it is a inclined, means there is a gradient, or we call as a more scientific way is a hydraulic gradient, then transmissivity is going to be the transmittive value is going to be large. So, sometimes it is used as convenient quantity in the calculation of groundwater flow instead of hydraulic conductivity. So, we started with the porosity, then permeability, and then hydraulic conductivity. Now, we are moving towards the transmissivity. So, we also use this word, and this is how it can be defined. The transmissivity is denoted with T, and the coefficient of permeability which we have discussed just K are related to each other. That is the T, the transmissivity is equal to K and H. H is the thickness, saturated thickness of the aquifer. So, it is a direct relationship of the transmissivity with the coefficient of permeability and the height or saturated thickness of the aquifer. So, here hydraulic conductivity or coefficient of permeability is the rate of flow under a unit hydraulic gradient through a unit cross sectional area of aquifer, and here it is shown as A, that you can see in this figure that this is the opening. So, this example is here. So, this is the unit cross sectional area through which water will flow depending on the gradient and other things. So, now we are basically moving to try to understand or going to define the Darcy law. So, second is of course, the water is moving like this. So, transmissivity, whereas the transmissivity is the rate of flow under a unit hydraulic gradient through a unit width of aquifer of the thickness. So, in the here this is the transmissivity scenario which is also shown here. So, now as we have seen that hydraulic conductivity is a measure of material's capacity to transmit water. So, it will depend on the materials also, and it is defined as constant of proportionality proportionally related with a specific discharge of a porous medium under a unit hydraulic gradient, and in that is what we discuss in Darcy law. So, here V equal to minus K I, where is the V is a specific discharge and that can be given in the liter per unit time, and K is the hydraulic conductivity, that is L upon T again. So, that can be given, that means the L for length upon time, and I is the hydraulic gradient. The gradient has to be always considered, because all the time you do not have the flat terrain scenario or flat rock, because there may be inclined rocks are there. It is not all the time we will get the flat. So, therefore, this hydraulic gradient must be considered in any such calculations or estimations. So, we know that the hydraulic conductivity, which is a function of water viscosity. Now, go for further improvement in simple relationship. Now, we have to bring the viscosity and density, and we know that these values, especially the viscosity, will change with temperature also. Anyway, that will also come. So, water viscosity and density is in a strict sense a function of water temperature, I just mentioned, and however, given the small range of temperature variations, this we have also discussed that the groundwater temperature does not vary as the surface water temperature varies. But even then, for better calculations, because in some places the temperature changes or the temperatures are varying with time or with season. So, this temperature variations encountered in most groundwater systems, and the temperature dependence of hydraulic conductivity is often neglected. And if that is not counted, especially in those places where the temperature varies with season, huge variations are there, then we have to count. So, therefore, it is also an important parameter, because it controls the viscosity and also density of water, and it can influence to some extent. So, as we have seen that the transmissivity rate of flow under a unit hydraulic gradient through a unit width of a square of a given saturated thickness, and now transmissivity of an aquifer is related to hydraulic conductivity, which is as a relation T equal to Kb. And so, now here we are having the transmissivity T, and that is L square upon T, and B is the aquifer thickness or L also in that sense, length or thickness. Here we are talking about the thickness of the aquifer. So, again there is a direct proportional. Now, there are some in different as we have been saying that different material will behave differently, or permeability or hydraulic conductivity would be different in different material. So, first we are taking example of unconsolidated sedimentary materials, and so on the left side we are having like gravel, coarse sand, medium sand, fine sand, silt, loess, till clay and unweathered marine clay. So, if you see here that the hydraulic conductivity is in case of gravels is the highest one, which you can see here, and whereas in case of our unweathered marine clay is not very good from permeability point of view. So, it is having the lowest hydraulic conductivity, and rest of the materials are falling in between. So, if we say that I am getting a medium sand, then we may expect, depending on the compactness, sorting and other things, nonetheless we can expect that it would be in the range of 9 multiplied by 10 to power 7 to 5 multiplied by 10 to power 4. That kind of course meter per second. So, that kind of hydraulic conductivity we expect depending on the unconsolidated sedimentary materials. If we come for the compacted sedimentary rocks which have formed because through this initially uncompacted, then got compacted. So, typical sedimentary rocks are there. So, first if I take the example of a cast or a limestone terrain, reef limestone or these things. So, here of course, the hydraulic conductivity is going to be very high, whereas the shale which are product from the mostly clay. So, clay material does not have much hydraulic conductivity and rest values are in between. So, generally what we get say sandstone. So, it is having in this range, or also we get siltstone and other things, and limestone and dolomite cast is dolomite terrain is also in our country limestone. So, there the hydraulic conductivity is good, though exploiting water resources or groundwater from karst terrain, karst topography, or which is a where the solution activity has taken place, lot of caves and sinks and other channels have been developed. There it is really challenging to predict where water will be available, though lot of water is there, and the water moves also very fast in this kind of these like karst and limestone. There the water moves, as you can see the hydraulic conductivity, but finding water and exploiting water is challenging, whereas in case of say sandstone, siltstone, this is much easier. Now we come to real known hard rock terrain, or we say crystalline rocks. So, in case of crystalline rocks like permeable basalt, I have been giving this example earlier also, that the Deccan trap basalt which is there in large part of India covering Maharashtra, Madhya Pradesh and Gujarat, where the permeability may be high, hydraulic conductivity may be high like here relatively compared to unfractured igneous and metamorphic rock. Means these are the lower part, these are unfractured and they do not have much interstices or gaps or weathering at all. So, they are really solid rocks, hard rock. This is what we say typical hard rock, and therefore, this hydraulic conductivity value is going to be very low. However, the permeable basalt and basalt again is here. If they are vesicles and if they are not connected, then it will come here, but if they are vesicles and they are connected, then it will come as permeable basalt. So, all because people have estimated about this Deccan trap, there are 40 flows of basaltic rocks at some places, maximum 40 layers or 40 flows have been identified. So, that means every episode of this basaltic flow or lava flow must have created different kind of basaltic rocks, starting from permeable to much less permeable rocks like typical basalt. So, it is another challenging area to get water there or exploit groundwater from these areas. But if luckily if we get the permeable basalt, that is the even better than the fractured igneous and metamorphic rocks. So, it depends. So, that is why in case of groundwater studies, when people are looking for groundwater, they must study the rock types, what kind of rock types are there, that will sufficiently indicate whether what would be the availability of water in these rocks. So, overall hydraulic conductivity of some selected consolidated means solid rocks, hard rocks, and unconsolidated means might be loose materials of geologic kind. So, what we see that these are all solid rocks which are shown in the blue color, and these are the unconsolidated material which are shown here in red color. So, if we go through limestone and with solution openings, it is having a very good hydraulic conductivity, highest in this example, and unfractured igneous or metamorphic rocks we have just discussed will have very little, it is just at this stage. And similarly, clay will have also low hydraulic conductivity, and whereas the gravel will have the highest among these unconsolidated material. We expect that high hydraulic conductivity. I gave the example of like Doon Valley deposits are there. It is a large area of Himalaya where this the valley is filled with gravels and the hydraulic conductivity is very high. Sometimes there is a water problem because of high hydraulic conductivity. As soon as the rainfall occurs, all water goes downward and you do not get the shallow aquifer conditions. Anyway, so this kind of basically the geologic conditions are controlling hydraulic conductivity. And if we come back again and start linking with permeability, so unconsolidated material are generally more permeable than corresponding rock. Compare sand with sandstone, or for example, so sand is a loose unconsolidated material, sandstone is a consolidated. And similarly, the coarser material are much more permeable than finer ones, and the least permeable rocks are unfractured, intrusive, igneous, metamorphic rocks, which bear cool down very slowly, and which are really solid, which doesn't have vesicles, which doesn't have pore spaces, and therefore may not have much weathering or fractures, and therefore they are poor permeable rocks are there. Another unfractured lime mudstone also are having problem because they are made from clay. Sandstone and clay may have better permeability compared to unfractured intrusive rocks. So, permeability of sandstone can also vary. Of course, this we have already discussed as per the porosity, that widely depending on the degree of sorting and amount of cement that is present. So, when a sand becomes a consolidated, becomes sandstone, and sandstone if does not have much cementing material, then permeability would be high. But if it is really compact, having all pore spaces have been filled with cementing material, then obviously the permeability is going to be less. Further, fracture igneous and metamorphic rocks, especially fractured volcanic rocks, can be highly permeable. So, volcanic rocks example I am giving is about like basalt, which is present in a large part of India, and there might be in case of limestone, because of solution activities, there might be dissolved along fractures, bedding planes, and large openings can be found in case of mine. So, if we take examples of like a sand here and clay here, you can see that why the clay porous but not permeable. So, the clay or clay stones, silt, they are porous but not permeable, because the material is so fine that as soon as it comes in the contact with water, it swells and does not allow water to flow from one end to. So, both sand and clay deposits or their sandstone and mudstone are quite porous, 30 to 50% for sand and 40% to 70% for silt and clay. But while sand can be quite permeable, clay, mudstone are not. So, porosity may be high, but permeability is poor. So, connectivity has to be there. The surface of most silicate minerals and grains has a slight negative charge due to imperfections in the mineral structure. So, now we are talking about how permeability is influenced because of mineral structures, and that is especially in case of silicate. So, these are the slightly negative charge particles. So, like water is a polar molecule, and so that means that the while it has no overall electrical charge, neither positive or negative, one side of the molecule has a slight positive charge, the side with the 2 hydrogens, compared to a slight negative charge on the other side. So, this also affect in if you say in microscopic scale, it also affects our permeability. So, water is strongly attracted to all mineral grains and water within that bound water layer. So, a few micron around each grain is not able to move and flow along with the rest of the water. If that means that if rocks are wet or minerals inside the rocks are wet, then all the water cannot move. Some water will remain in contact with the grains, they are there. So, as I have already shown through this diagram that the example of sand and silt, clay, that the bound water is represented by dark blue line all along with each grain, and the water that can move to the light blue areas. In the sand, there is still a lot of water that is able to move through the sediment. But in the clay and silt, most of our water is held tightly to the grains, and this reduces the permeability. So, how the different grains are allowing water to move through openings, that depends on what kind of material they are made from. So, we have now seen that there is a wide range of porosity in the geological materials and also equally more wide range of permeabilities. There groundwater exists everywhere, there is a porosity. So, water will be there, but may not be permeable. However, whether the groundwater is able to flow in a significant quantity depends on the permeability, and the aquifer is defined, as we have already discussed this part, a body of rock or unsaturated sediment that has sufficient permeability to allow water to flow through. So, unconsolidated materials like gravel, sand, even silt make relatively good aquifers, and so rocks are like sandstone. And the best example of unconsolidated material which we get in Indo-Gangetic plain are mostly sand, sometimes you may get gravel and even silt. So, these are good from that point of view. The other rocks that can be good for good aquifers, which must be fractured, well fractured, weathered. Granite can be one of the examples, or basaltic terrain can be example. Whereas we know that aquitards, a body that does not allow the water. So, this is another end of another extreme in case of types of water, types of aquifers, and aquitard generally made from clay, till or poorly fractured igneous metamorphic rock. Till we have discussed in previous discussion, which is a very poorly sorted loose material. So, these are relative terms, not absolute, and are usually defined based on someone's desire to pump groundwater. Which terms? Permeability, hydraulic conductivity and transmissivity. And what is an aquifer to some what does not need a lot of water may be an aquitard to someone else who does. So, it depends that what kind of output from a well is expected. So, an aquifer that is exposed to ground surface is called unconfined aquifers. This part we have already discussed. An aquifer where is a lower permeable and bottom permeable, higher permeable is there, then we say is a confining layer. So, aquitard is a body which does not allow transmission of a significant amount of water, and these are the relative terms which we have already discussed. So, now we see through a cross section there are series of rocks and unconsolidated materials, and we can see here there is a unconfined rocks, then confining layers, then confining aquifers, and then you are again getting a unconfining layer. So, there are confined aquifer conditions are there, and so what it shows that some of which might serve as aquifers and others are aquitard or confined layer, confining unconfined aquifer at the top and confining layer is basically aquitard, and the granite is much less permeable than the other materials and is so as aquitard in context. So, sometimes like here it is shown also granite, and hydraulic conductivity value is also shown here, and these different rocks hydraulic conductivity is also shown here. So, when hydraulic conductivity is good, like in case of this yellow confining aquifers, good, here unconfined aquifer not that bad, but quite good, but here the value is very low confining. So, the permeability is less, hydraulic conductivity is less. So, yellow layer is here is the permeable and would make an ideal aquifer, and overlaying grey layer as we have seen is having though it is confining, but same time it is behaving like a aquitard, not much permeability is there. Whereas the upper buff colored which is showing the does not have a confining layer and it is a unconfined aquifer conditions, they get easily recharged with the rainwater, but if there is no other source of recharge, then these wells, if they are in the unconfined aquifer conditions, will go dry in dry season, may go dry in dry season. So, yellow layer we have seen that the hydraulic conductivity is shown as K, that is 10 to power minus 1, and confined, and whereas in confining layer that value permeability value or hydraulic conductivity value is very less. So, now when we move, one more term we would like to bring here is the intrinsic permeability, or we say permeability is a quantitative property of porous material and is controlled solely by pore geometry, and it is independent of fluid viscosity and density. So, intrinsic permeability parameter can be used when it is not getting influenced because of temperature, viscosity and density. So, it is the soil's hydraulic conductivity after the effect of fluid viscosity and density are removed, and then it becomes intrinsic permeability. Or in roughly you can say that inherent permeability, as we have also say like primary porosity. Here it is the character of the rocks rather than fluid. So, the characteristics or varying characteristics of fluid is removed, that is the viscosity and density through discussion or in calculation. So, it is calculated as conductivity K multiplied by the fluid viscosity divided by fluid density and the gravitational constant. So, permeability K has the dimension, as you know, of the area in a cubic centimeter or cubic meter, and a saturated hydraulic conductivity is a ease with which the pores of a saturated soil transmit water, that part of aquifer which is completely saturated, or that part of a rock layer. So, it is expressed in micrometers per second. Historical definition of saturated hydraulic conductivity is the amount of water that would move vertically through a unit area. So, here now we are talking about vertical movement of a saturated soil in units or unit hydraulic gradient. So, this becomes important in case of groundwater recharge structures or in that estimations. So, saturated hydraulic conductivity is used for soil interpretation. It is also known as K sat. Now, we will see the comparison of saturated hydraulic conductivity and intrinsic permeability. So, as we can see that saturated hydraulic conductivity Ks is temperature dependent, and whereas intrinsic permeability is now completely independent of temperature variations. Similarly, it is fluid viscosity dependent, the saturated hydraulic conductivity, whereas in contrast regardless of fluid viscosity unless the fluid itself changes soil structure. So, if fluid itself, if polluted water or other thing, then there might be. So, this is a temperature independent, also the viscosity independent, and changes with change in structure, and both are changing with structure, means depending on the pore spaces, interstices, gaps, fractures and so on. Dimensions depends on flux and gradient. Gradient is always important and time is component, time is a one component, and here dimensions are given in the square length or square centimeter, which is a unit area, and time is not a component here. So, this is what the difference between saturated hydraulic conductivity and intrinsic permeability. It depends on where, for what purpose we are using these parameters, accordingly we will use. So, with this I end this discussion about permeability. Thank you very much.